So good afternoon, everyone. Thank you for joining us this afternoon for our second webinar of the webinar series for Project LAMP. My name is Jorge Reyes, and I'm the project coordinator for Project LAMP, a USDA NIFA-sponsored project under the name Optimizing the Cost Effectiveness of Lighting and Control Environment Agriculture. Through Project LAMP, our team is helping growers get more value out of the lighting system by providing horticultural and economical information, providing tools to manage lighting for optimal crop growth and quality, and of course, to maximize the return on investment. Without further ado, and without any more details, let me introduce to you Dr. Josh Craver and his PhD student, Anthony Percival, who will also be sharing some of his research in this talk and assisting Dr. Craver. Dr. Craver is an assistant professor of controlled environment agriculture in the Department of Horticulture and Landscape Architecture at Colorado State University. His research focuses on enhancing vegetable and floriculture crop production in controlled environments, and in Project LAMP, Dr. Craver assesses plant photobiology, lighting optimization for both greenhouses and indoor production of floriculture crops using LED lights. Dr. Craver, the room is yours.
Thanks so much. Let me see if I can share my screen real quick. Excellent. Thank you so much for that intro. I had my grad student, Anthony, here. He's joining me as well. This is all the research that we have been doing over the past few years as part of Project LAMP. So we are really excited to be sharing some of our work. Okay, let's leave that be. That's fine. And so, yeah, what I'll be talking about today is a lot of the research we've been doing on end-of-day lighting. And so really with this presentation, the goal is that hopefully we're able to highlight a bunch of the research, but also definitely has a lot of application for growers. And so we'll actually start out with a lot of background that'll help with just understanding the basics of what we mean by end-of-day lighting, photoperiodic lighting. And then as we transition into the research, we'll really lean into a lot of the questions we've been asking and ultimately end with a lot of deeper insights from Anthony. And so specifically as a webinar overview, I want to briefly talk about supplemental versus photoperiodic lighting, just laying down that foundation, talking a little bit more about end-of-day lighting and some of the applications that we see specifically for end-of-day light in the greenhouse, getting into some of our research we've been doing both in the greenhouse as well as in growth chambers, specifically looking at a bunch of interactions that we have with temperature. And then I'm going to pass the mic over to Anthony at that point and let him provide some deeper considerations and some future directions where we're actually continuing this research beyond what we've been doing as part of Project LAMP. A lot of lingering questions that you're going to see as we get through some of his work. And then lastly, I'll provide a brief summary at the end of this that's just good for takeaways, especially for growers that are looking at how am I using end-of-day lighting applications in the greenhouse? What are the things I should be considering right now? So with that, let's go ahead and jump in. And we're going to start just with brief background. I know with the audience we have on here right now, I don't need to give this background, but hopefully if some growers are watching that have some interest, this provides a good foundation. And so specifically with supplemental lighting, we know we're driving photosynthesis. The goal of this lighting is to reach target daily light intervals or DLIs. We have a variety of technologies that I'll talk about to do this, but ultimately for floriculture crops, we're often aiming for anywhere from 50 to 75 micromoles of light, supplementing that ambient DLI. Or for vegetable crops, we'll often aim for 100 to 200 micromoles. So again, it depends on the crop, depends on the species. But ultimately, we have a lot of different light sources we can use for supplemental lighting, ranging from high pressure sodium metal halide to many different LED options. What's really interesting about these options is that light quality does differ between them. And so if we look, for example, at our LED greenhouse over here on the left, this is actually at the CSU Hort Center, where we have red, blue LEDs. You can see our peaks in the red and the blue. Whereas over on the right, we've got high pressure sodium lamps that are more full spectrum, including a bunch of wavelengths, both in the lower red as well as in the orange, the green. And so again, while supplemental light differs in terms of light quality, generally the most important things in terms of supplemental lighting is just your output, the amount of intensity that's being provided. And so we find, and I'll talk about this a little bit later, that there are sometimes changes in terms of photomorphology that can occur as a result of the light quality coming from your supplemental lights, but generally the most important thing is lamp intensity, the light intensity. And so as a result, the most important aspects are going to be energy use, intensity output, efficacy, initial cost. These are all the things you should be thinking about as you're looking at what supplemental lighting source should I be investing in to install in my greenhouse. Light quality, again, certainly does play a role, but it often takes a backseat to many of these other considerations. Now, photoperiodic lighting, on the other hand, and we had a whole Anthony actually gave as part of Project LAMP a overview very similar to this of comparing supplemental lighting and photoperiodic lighting specifically. But again, as we all know, for photoperiodic lighting, generally we're looking at very low intensity light that's used to essentially manipulate the photoperiod, to extend the day or interrupt the night. And so commonly we use this for flowering of many of our crops. It's a great flowering technology where specifically the two most common are going to be day extension, where, for example, if our sunset occurs as you see here at 6 p.m., we can extend that day with a flowering lamp, photoperiodic lighting, to include an additional 4 hours to give the plant the perception of a long day. Or we can do things like night interruption, where we're going to break that long night up into 2 short nights. And similarly, that will stimulate that flowering response for a long day plants, or will inhibit flowering of short day plants. So basics of photoperiodic lighting, but what's important to understand here as we're comparing supplemental and photoperiodic lighting is that we have differences in terms of light intensity. So for photoperiodic lighting, anywhere from 1 to 4 micromoles might be recommended depending on the crop. And so very different, very low light intensity compared to what we generally provide at supplemental lighting. And so as a result, we go to great lengths to make sure it's clearly understood that photoperiodic lighting is definitely not a substitute for supplemental light. And so we really need to understand that we have two different purposes behind these. Supplemental lighting, we're driving photosynthesis, driving biomass gain, whereas for photoperiodic lighting, generally with the uses, we're looking at how we can manipulate flowering. To further drive this point home, though, I like to just include things like light response curves. And so specifically, if we look over here on the left, you can see a gas exchange system. For those that may not be familiar, this allows us to measure leaf photosynthesis. We can clamp onto a leaf and we can look at how photosynthesis, in this case, changes in response to PPFD, or light intensity. So what we see here is a light response curve where we have assimilation rate, net photosynthesis, or just photosynthesis on the y-axis. And then we have our PPFD, or photosynthetic photon flux, here on the x-axis. And what we would expect, and what we all know, is that as we increase that light intensity, we're going to see photosynthesis increase in response. And so generally, when we're looking at these light response curves, there's a couple of things that we can break down that can be really informative in terms of how our plants are responding to light. Specifically, we often refer to the light saturation point, or the LSP. This is going to be where further increases in light intensity don't result in an increase in terms of photosynthesis. So we see that the plant is saturating out. Additional PPFD is not further increasing photosynthesis. But importantly, for photoperiodic lighting applications, we also need to think about what's referred to as the LCP, or the light compensation point. And so the light compensation point is that point at which our net photosynthetic rate is 0. In other words, our gains from photosynthesis are compensating for our losses due to respiration, whether that's photorespiration or dark respiration. So as a result, why this is an important aspect to drive home is that when we're using photoperiodic lighting, we've had growers in the past that have said, oh, I'm using photoperiodic lights and I'm seeing increases in terms of biomass. I'm providing additional light for my plants in terms of photosynthesis. What we have to understand, though, is that this 1 to 4 micromoles of light that we're generally providing through photoperiodic responses is not nearly enough to reach even that light compensation point for most species. As a point of reference, if we look at, for example, a 2 micromole target in terms of photoperiodic lighting, if we were to look at the contribution that we're getting to DLI over the course of a 16-hour photo period, we would only be getting around 0.1 moles per meter squared per day in terms of a contribution to DLI. So very minuscule in terms of what we're able to provide to our crops. And so again, as a result, it's generally, driving home that point, not a substitute when we're looking at photoperiodic lighting compared to supplemental light. It's just not a high enough intensity to really drive photosynthetic responses. We did do some research on this, though, way back in the day. So this was before I joined Project LAMP, about a year before I joined LAMP, where we were looking at some similar questions. This was with my previous advisor, Dr. Roberto Lopez up at Michigan State University, where we had a project. We were looking at a lot of different aspects of lighting, but one of those was we were looking at responses under photoperiodic light. And what you'll see is that we were doing some comparisons, and specifically we had HPS and LED supplemental lighting that was being provided to many different annual bedding plant species, anywhere from 70 to 90 micromoles. But we also had flowering lamps. So what you can see here is we had our HPS, and you see that typical spectrum for an HPS lamp. We also had our LED supplemental lighting. Both of these were providing 70 to 90 micromoles. And then we had our 2 flowering lamps. And you can see here there's some differences in the flowering lamps in terms of the peak red compared to the peak red and the peak far red. This was a red, white, far red flowering lamp, which we're going to talk more about as we continue to move into this presentation. But ultimately, what we found is what you would generally expect, and was great for us to drive this point home to some growers who were still continually thinking photoperiodic lighting was an effective means of supplemental light, that it was a good addition to their to their supplemental lighting. Specifically, this is a massive amount of data that I don't want to work through. I just want to drive home one main point. Specifically, if we look at these top 4 bars, we can see HPS and LED, and we're providing 70 or 90 micromoles of supplemental light. And if we just look at petunia as our example here, we'll see that what's referred to as the quality index increased under supplemental lighting. The quality index is an amalgamation of it's an equation that's taking into account shoot dry mass, fruit dry mass. It's also looking at the caliper, the sturdiness of a seedling. And ultimately what we found across the board was that under supplemental lighting, all of those quality attributes were increasing. When we grew plants, though, under this photoperiodic lighting throughout the photoperiod, adding those additional 2 to 4 micromoles, what we found was that quality was actually very similar to just providing no light at all. You can see our natural lighting is the black bar here. So as a result, we have this great discrepancy in terms of quality that occurs as a result of just not providing the same amount of photons. We're not providing enough photons to really contribute in terms of supplemental lighting in this case. What we do find, though, and what I want to transition to talking about for the remainder of our talk here today, is we do find there are photomorphogenic effects or morphological effects as a result of end-of-day lighting or photoperiodic lighting. Specifically, if we look again at petunia, but also in patients here, we'll notice we're looking at leaf area now, and that in response to photoperiodic lighting, we do see increases at times in response to that photoperiodic lighting for parameters such as leaf area. And so this is something that's important to consider, is that even though photoperiodic lighting isn't contributing significantly to your DLI, even though you're not going to see these huge gains in terms of photosynthesis, it's not just used for flowering. Like it's just because it's not contributing to photosynthesis doesn't mean it doesn't contribute, in this case, to morphology. And so specifically, photoperiodic lighting is not just a means to control flowering, but can also impact morphology, vegetative growth, as well as pigmentation. And there's a ton of, the list can go on and on as we kind of discuss the nuances of each of those. But it's important for us to understand the impacts that photoperiodic lighting, including end-of-day lighting, can have. And so one of the things that Anthony and I have been working on as part of Project LAMP is looking at end-of-day lighting specifically and saying, how can this be valuable for greenhouse production? How can we leverage end-of-day lighting to achieve certain outcomes in the greenhouse? And so specifically, we've been looking at end of day, which is a form of day extension, where we're extending that photo period past when the sunset occurs. And specifically, we think end of day lighting may be a valuable option in the greenhouse for a couple of different options. One is that light quality control in the greenhouse is often very difficult to achieve during the day. So a great example, again, if we look at the Hort Center that we have here at the Colorado State University, we can see our red-blue LED lighting that makes up the majority of the spectrum. These are Philips top lights that we have installed at the Hort Center. And you see that red-blue spectrum that we get during the middle of the night when we have no ambient sunlight. But in the middle of the day, most effects that we would generally see from a plant responding to red and blue wavelengths of light at different proportions, those are often bleached out or not as evident because we have so much ambient sunlight. And so, for example, adding a high blue spectrum from supplemental lighting, that's potentially only 70 micromoles of overall, potentially hundreds of micromoles that we're receiving over the at midday in a greenhouse. And ultimately, we're just not going to see the responses we would normally expect as a result of supplemental lighting not contributing significantly to spectral shifts. And so as a result, we can look at end of day lighting and say, can we just apply certain spectrums of light at the end of the day? And can that initiate some similar photomorphogenic responses that we might be able to benefit from in our plants? Additionally, what's important about end of day lighting that separates it from supplemental lighting is that it's applied at very low intensities. And so a lot of what we've been looking at is, can we use very low intensity light to potentially manipulate plant morphology and instigate some beneficial responses? And so end of day lighting is something that we've been focusing quite a bit on in our lab. And so specifically with end of day lighting, though, we're using commonly flowering lamps, and flowering lamps come in a lot of different spectra. And so you'll see a breakdown here. This is a great figure that was put together by Runkle and William Mung up at Michigan State University at the time. William's now at University of Delaware. But what you see is that we have multiple different photoperiodic lamps, and those all emit different spectra. Some of them include far red light, some have different proportions of red and blue. And what's critical here is that these different spectra of these photoperiodic lamps aren't just manipulating, in this case, flowering, they also have a lot of impact on morphology, or they can have a potential impact on the morphology of the crops that we're producing. One of the things that I mainly want to focus on, though, is specifically far red light. And so you'll notice I'm showing this figure again of the study that we ran back at Michigan State University. This was back in 2019, where we were looking at red-white flowering lamps as well as red-white far red. And so you can see the inclusion of that far red light here in that red-white far red flowering lamp. And so what's important to understand is that some plants do have what's referred to as an obligate a far red response. They need to have far red included in the spectrum to flower, or it might be a facultative response where they flower more quickly when they have that far red included. But what's interesting is that that far red light included in that spectrum can cause a lot of photomorphogenic responses. And some of those responses are things that we've been wanting to try to capitalize on in terms of greenhouse production. So before we get into that, though, I want to briefly just talk about far red specifically, because this is something that's often manipulated in terms of flowering lamps and something that's been the focus of a lot of our research. And so far red radiation, as I'm sure for the many talks that you all have heard, know now, both growers and academics alike, we're talking about 700 to 800 nanometers. And so that's the wavelength range. It falls just outside of the visible spectrum, or right on the edge of the visible spectrum, so we can kind of see far red. But as we move further up in that spectrum, it becomes very dim to our eyes. But flowering responses is what we generally associate with far red light. Again, far red is commonly included in many of our flowering lamps as a result of its potential and requirement in terms of flowering. But we see that far red light is not just important for flowering. We actually now have many different definitions of far red light. And I know Nate Island's next, or in a few weeks for the next LAMP webinar, is going to be talking more about far red light specifically, and talking more about the impacts that it has. So we're going to talk about one aspect of far red light today, but just in terms of ranges, far red light 7 to 750 nanometers is incredibly important from an EPAR perspective. And so there's been a lot of research done and still being done looking at extending our definition of photosynthetically active radiation to now include those 50 additional nanometers of far red light and their important role in terms of specifically photosystem 1, but we're not going to get into that today. But just knowing that far red light is not just being found to now be involved in flowering and photomorphogenesis, but is also driving photosynthesis. But more importantly today, we're going to be talking more about far red light and its uses in terms of photomorphogenesis. And so looking at specifically shifting the red to far red ratio like you see in this picture that we have over here in the bottom right. So far red light's an important environmental signal that affects morphology, including shade avoidance, which is one of the things we're going to be focusing on, as well as flowering, photosynthesis, and many other responses. When we're talking about photomorphogenesis, though, the one that I really want to focus on is red to far red ratio. And so the ratio of red to far red radiation, you can see all we're doing is taking red light, 6 to 699 nanometers, dividing by far red light. And it's a common metric that we're using to characterize the degree of shade. And so a practical way to look at this is we have this nice figure over here on the right where we see daylight. Now, if we were to walk outside right now in terms of daylight, we would have a red to far red ratio of somewhere around 1.3. And so what's interesting is that that red to far red ratio is going to cause plants to perceive that ratio and say, I'm in sunlight, and they're going to respond accordingly in terms of leaf area expansion and development. What we're going to notice, though, is that as we move deep into canopies, what happens is that plant leaves, those canopies are going to absorb red radiation, and far red radiation is going to generally penetrate deeper. Less of that far red light's absorbed. As a result, as we move deeper into canopies, you see that our red to far red ratio shifts. We actually get a much lower red to far red ratio. So 1.3 in daylight, you can see a much filtered, much lower red to far red ratio here of about 0.07. And this is an incredibly important way that plants perceive shade. In this case, we have a myriad of shade avoidance responses that specifically occur as we shift or decrease that red to far red ratio. And so we see these including things like stem elongation, internode elongation, petiole elongation, thinner leaves, reduced branching. The photo over here on the right is of some impatiens that were taken years ago, and you can see that red to far red ratio is reduced because those plants are spaced too closely together. And so they're perceiving deep within that canopy a low red to far red ratio, causing them to stretch in response to that close shading and close spacing that's occurring in this greenhouse. But one of the responses that's also characterized as potentially involved in shade avoidance is leaf area. It can be pretty variable. It's not as easily, or it's not as characteristic as what you'd see with things like stem elongation and stretching. But there are many species that will respond to a low red to far ratio in terms of leaf area expansion. And that's something you're going to see in a moment that we've been focusing in on quite a bit with some of the research we've been conducting. And so just to further iterate this point, a low red to far ratio promotes shade avoidance. You can see some petunias that we have over here on the right, where we have a very high artificially developed red to far ratio. We're using electric lights to create this red to far ratio. So in that case, a red to far ratio of 11 compared to a red to far ratio of 0.5. And so what you can see with these petunias is characteristic responses. And we're getting petiole elongation, some leaf area expansion, and we're also getting thinner leaves, a reduced chlorophyll content, all very characteristic of a low red to far ratio. You can see in lettuce some very similar responses where stretched petioles, slightly thinner leaves, more chlorotic leaves. Well, what's interesting is that plants perceive these responses incredibly quickly. And so what you'll notice is we have our petunias here, and we have a red to far ratio on the left of 3.8. But as we shift that lower to a low red to far ratio of, in this case, 0.7, you'll notice the leaf hyponasty. Those leaves are starting to point upward, trying to capture more photons, responding to that shade. And this is a response that occurred in over the course of a day. And so plants are very perceptive and they'll respond very quickly to the environment that they're placed in this case of red to far ratio. So all this is driving home the point. And one of the things that we want to really bring home is we have all of these responses. We generally associate shade avoidance responses with negative plant quality, reduced plant quality. It's something we're often trying to avoid as growers in the greenhouse. But the question that we're wanting to ask is shade avoidance always a negative response? Are there ways that we can capitalize on shade avoidance to actually see benefit in terms of the environments that we're manipulating? And potentially harness some of these beneficial, or look at some of these responses as potentially being beneficial in the greenhouse. One of those is specifically leaf area. And so if we look at, for example, young plants, we generally have a very low, what's referred to as leaf area index. And so for those that may not be familiar, leaf area index, a simple way to think about it is if we look at this plug tray, if we look at this seedling that I just highlighted here on the bottom, you'll notice we have the cotyledons just emerging, no real true leaves. The amount of leaf area compared to the total area of the plug of the cell that seedling, that plug has to grow, very little leaf area, lots of exposure in terms of substrate as well as plastic in the area that we've designated for that seedling. And so leaf area index is going to be the centimeter squared of leaf area compared to the centimeter squared of the ground area in which that plant's being produced, in this case, a plug tray. And so what we can see, though, is that as that plant develops, as it grows, those leaves are going to expand. It's going to take over more of that total area. And why this is important is that that's going to improve, in this case, light interception. So commonly for the production of annual bedding plants, we're providing supplemental light to these crops throughout the winter months. We're commonly starting many of these plants in the very late winter, very early spring when DLIs are low. We're providing lots of supplemental light. But as a result, early in production, we have a lot of photons that are being produced from those supplemental lights that aren't intercepting plant material. They're hitting other parts of the canopy, or not the canopy, other parts of, in this case, substrate, plastic, anything but the plant. And so any photon that's not being intercepted by the plant, we can consider being wasted. And so one of our questions was, could we potentially use end-of-day lighting to help us expand these leaves early in production, to get some of this leaf area expansion, and as a result, to improve light interception early in production? You can see that this isn't just for annual bedding plants. We see common responses in hydroponic crops as well, where if we could get earlier leaf expansion, we could close up those canopies, improve light interception, and as a result, hopefully improve light use efficiency in terms of how we use our supplemental lights and intercept those photons. But we have to understand that using end-of-day lighting, specifically end-of-day far red lighting, can lead to those undesirable responses like what we saw with lettuce. And so it really becomes a question of how do we use this? How do we leverage end-of-day lighting, specifically end-of-day far red lighting, to stimulate these responses that ultimately we want to see? And so before I head into the research, the last background slide I have here is just about far red LEDs and why we're starting to see more application for some of this research here in the recent years. And so specifically, when we look at far red included in LEDs, we often have full spectrum or white LEDs that are being produced now, where far red's already included in the spectrum. So you actually see an example of this with the Fluence LEDs that we have over here on the right. These are some LEDs that we've installed in our growth chamber, but many growers will install these in mostly vertical or sole source lighting scenarios. What you can see here is that this is white light. We're measuring from 400 to 800 nanometers. It has a spectrum very similar to what you're seeing down here in the bottom left. I'm going to reference this figure again in just a moment. But we can see far red that's included in what's otherwise a fixed spectrum. You can turn that LED on, dim it on or off, and you're going to see all the wavelengths of light adjust accordingly based on that fixed spectrum where far red's included. We're seeing more and more, though, that far red can both be independent fixtures. And so in this example in our growth chamber here, you'll actually see we have independent fixtures that only emit far red light and allow us to manipulate far red independent of an otherwise fixed spectrum. So this allows us to start manipulating that red to far red ratio, where generally it was a little bit more difficult in the past. But we're also seeing adjustable options. And so with our far red, you can see in this case, those independent fixtures looks pretty dim to our eyes. That's at maximum intensity in terms of far red light. But again, difficult for our eyes to see. What we're seeing is that fixtures that are currently being placed on the market that we're seeing installed in greenhouses now have adjustable spectrum. And so, for example, we have this heliospectra. We've worked quite a bit with heliospectra in terms of our research and using many of their fixtures. What you're seeing is this is the Mitra fixture that they have, where not only do they have a channel that's providing a full spectrum white spectrum of light, but they also have an independent far red channel that allows you to manipulate, in this case, how much far red light you provide to your crop throughout the day or potentially at the end of the day, and gives you control over, in this case, the red to far red ratio. And so we're seeing technologies now on the market that allow us to capitalize on some of these responses, but we need to understand how to really develop good protocols for is end of day lighting effective in terms of manipulating photomorphology and how we can really capitalize on some of those benefits. So what this leads us to then is a series of experiments. And so I'm going to talk briefly about 2 experiments, and then I'll pass it off to Anthony to talk about some of the directions we're heading based on some of the results we found from these early studies. But ultimately, when we look at end-of-day far red lighting, what we first wanted to do was just look at some applications in the greenhouse. And we wanted to look at, could we leverage end-of-day far red lighting to get early leaf area expansion, looking at a wide variety of, in this case, annual bedding plant species. And could that potentially be beneficial in terms of intercepting more photons, driving more efficiency in terms of supplemental lighting? And so what we did was we applied end-of-day far red light. We used flowering lamps like you see over here on the bottom right, but then we also used, Elixia fixtures that you can see over here on the bottom, and these gave us very discrete wave bands in terms of far red, so that we could provide very specific red to far red ratios. And so as a result, we were able to manipulate the intensity in terms of how much light we provided for an end-of-day far red application, how long we provided that end-of-day far red application, and also ultimately the red to far red ratio. And so lots of adaptability that we could look at what's ultimately influencing these responses. What we found in this early research, though, if you look, this is a simplified figure. We had a ton of treatments. Anthony has taken these figures and really simplified them to drive home a couple of key points. And so what you'll notice here is we're looking at stem length, in this case for petunia. And so specifically, this is 2 cultivars of petunia. I accidentally axed out the other half, so we'll look at that in just a minute. But it's Dreams Midnight and Wave Purple. Dreams Midnight's the blue, Wave Purple's the orange. But what you'll notice is that we have a control, and then we have 3 different end-of-day treatments. An end-of-day treatment with a red to far red ratio of 0.8, of 0.15, or of 0.15. And additionally, you can see different durations of 30 minutes or 4 hours. What we found was that we got quite a bit of stem extension, stem length from petunia at the seedling stage in response to an end-of-day far red application at a low red to far red ratio. If we gave it to them for a 4-hour duration, it was quite a large dose, in this case of end-of-day far red. You can see that as we shortened that duration or decreased the dose, that we did see less of that stem extension as a result. Unfortunately, though, from the study, so there's the Dreams Midnight and the Wave Purple. Unfortunately, we didn't see an impact in terms of leaf area index. We saw a lot of stretching as those plants were stretching for that under that perceived low red to far red ratio or perceived canopy that they believed they were under. But in this case, we didn't see an expansion in terms of leaf area. Across the board, it was not significant. And so what this led us to start to ask questions, and we saw this in many different species, similar responses, is first of all, we found that these end-of-day far red responses seem to be very specific to species as well as cultivar. They all respond slightly differently to these end-of-day applications. But specifically what we noticed in the greenhouse was that a low DLI may be limiting some of the morphological responses. And unfortunately, in this case, we were growing these plants in a greenhouse. We had a generally low ambient DLI that these plants received over the course of the study. In many cases, it was 5 or less. And so as a result, we may have just not been giving the plant enough resources to put some of those resources into leaf expansion. And so one of the things we wanted to do was actually shift this over out of a greenhouse into a growth chamber to better characterize some of these responses in terms of, in this case, DLI, but to also start to bring in some questions around temperature. Because what we find is that far red light and temperature actually work somewhat interactively. And that further complicates some of these applications that we may want to develop in the greenhouse or potentially in an indoor production environment. So I briefly want to talk about far red light and temperature and then show how we've been doing some follow-up work with some additional research. And so specifically, when we look at end-of-day far red light, you can see here phytochrome. We have an inactive and inactive version of phytochrome. And so in this case, it's all driven by red and far red light. And so you can see as we have a higher proportion of red light, we're going to shift from the inactive to the active form of phytochrome B in this case, and that's going to inhibit shade avoidance responses. But as we have more far red light that generally occurs towards the end of the day or at night specifically, we have a shift that occurs back into the inactive state where we don't have an inhibition of those shade avoidance responses, so we'll generally see those characterized. So that's why a high red to far ratio shifts us more to that inactive, or sorry, a low red to far ratio shifts us into that inactive state, causes more of these shade avoidance responses. What we find is that it's not just red light and far red light, but also temperature. Warmer ambient temperatures and far red radiation promote similar responses in terms of taking that active form and shifting back to that inactive form of phytochrome. And specifically, PFR, or the active form, is going to revert faster back to that inactive form as temperatures are increased or under those warmer temperatures. This is relevant to greenhouses, and so specifically for growers, we're commonly using DIF. We use DIF to control elongation responses in many of our plants. You can see, for example, the lilies that we have over here on the right, negative and positive diff, where we have a higher day, lower night, leading to taller plants. Generally, we can suppress some of that growth or that elongation under a negative diff, where we would have, in this case, a lower day, higher night. But we're already manipulating temperature, in this case, to control stem elongation in many cases in the greenhouse. But what's interesting is now we have this combination of, it's been shown in previous literature that end of day far red can enhance positive diff response and actually overcome negative diff treatments. And so we have an interesting interaction that occurs between far red light as well as temperature. And this is something that we wanted to explore further to really understand what are the implications of your ambient air temperature as you're trying to manipulate or use end of day far red or far red during the day. This is some research we've worked somewhat in tandem with Texas A&M. I know some of you have maybe seen Shuyang Zhen's work, where they've been doing far red throughout the day and looking at different temperatures, and she was doing a lot of that as part of Project LAMP. We were really looking at a lot of the temperature responses, but specifically focused on that end of day application, in this case of far red light. And so specifically what you'll see here is this is some preliminary data that we had on lettuce, and I'm going to show some of the studies that we ran immediately after that. But what you'll see is we have 2 cultivars of lettuce. You can see Salanova red oak leaf as well as Rex. And we've got all of our different treatments here at the bottom. And so in this case, we've got a control where plants were just grown under normal full spectrum LEDs at 21 degrees Celsius. Then we had an end of day far red treatment at 21 degrees Celsius. And then we had far red applied throughout the day at 21 as well as 16 degrees Celsius. And then we had an end of day far red under 16 degrees Celsius and an end of day far red under a positive diff. It's a lot of different treatments, and mainly the takeaway that I want to show is just the degree of photomorphogenic response we get in response to both an end of day or far red throughout the day, as well as the manipulation of temperature. And so specifically, you can see that when we apply that far red light throughout the day, like you see with our 2 seedlings in the middle, you get a lot of that elongation, a lot of that expansion growth as a result. Whereas when we apply it as an end of day response, it's a little more moderated. You don't see quite as much expansion growth as a result. But temperature helps to, in some cases, interact with and control some of that growth. You see some suppression of growth, but also some potential interactive effects of, in this case, temperature and far red light. So that's what we really want to explore. And I'm going to talk a bit more about this as we move forward and discuss a second study that was run specifically on lettuce. We ran a very similar version of this study on petunia. And just due to time today, we don't have time to go through all of it, but I want to briefly talk about some of the work we did with lettuce. And so specifically, you see that in this case, we wanted to grow the plants under a sufficient DLI for seedlings of about 12 moles of light. And we had a photo period of 16 hours, but then applied 2 different end-of-day treatments for 2 hours each. And so in this case, instead of having a true, in this case, control with no end-of-day lighting, we actually just had a control, which was end-of-day white light, and then we had an end-of-day far red light. And the importance between those two is just the red to far red ratio. One had a much higher red to far red ratio, in this case of 3.76. The other a much lower red to far red ratio of 0.7. So we call the low ratio our end-of-day far red treatment. We're providing a lot of far red light to those crops. And so here you can see a breakdown where we then combined these end-of-day treatments with temperature. And so specifically, you can see we had both of those end-of-day treatments at an ambient temperature of 23 degrees Celsius, an ambient temperature of 18 degrees Celsius, or we had a positive diff treatment where we grew the plants under the 23 degrees Celsius during the day. And then once we switched to our end-of-day treatment and throughout the rest of the night period, we dropped it to an 18 degrees Celsius temperature. So look at that interaction that may be occurring, in this case, between far red lighting application and temperature. And so to briefly run through some results, what we found was that end-of-day far red light did have an interaction with temperature, specifically in terms of leaf area. And so there was a promotive effect of that end-of-day far red light at the ambient temperature of 23 degrees Celsius. So we can see here that we do get an increase in leaf area, albeit relatively moderate, not quite as dramatic as what we would have maybe expected. But we still get an increase in leaf area, but that was only really characteristic at 23 degrees Celsius. We saw much smaller differences at 18 degrees Celsius, which are probably in part due to just really slow plant development that can occur under those low temperatures throughout the entire production period. Specifically, though, when we look at individual leaf area, we did find that end-of-day far red, regardless of treatment, did promote an increase in leaf area. And so you can see here that if we just take temperature out of the equation entirely, that application of end-of-day far red compared to end-of-day white did result in an increase in individual leaf area. So this is where we took total leaf area divided by the number of leaves. But again, the degree of that response was relatively limited. There was some, we would have liked to maybe have seen in response to that end-of-day far red treatment a little bit more expansion that the crops could have benefited from, but still some expansion that occurred as a result of that end-of-day far red. Another interesting aspect of this, though, is anthocyanin content. And so specifically, we measure total anthocyanin content. And what you can see here is that because pigmentation has been shown to also be manipulated by far red light, specifically end-of-day far red. What we found, though, is that end-of-day far red did not impact, in this case, total anthocyanins. What really was driving the responses was temperature. And so to help drive that point home, if we go back and look at this figure that we were talking about earlier, we can see some of the characteristics that we would normally expect in terms of an application of far red and potential impacts on pigmentation. And so here you can see a control compared to end-of-day far red. There have been some studies done that have shown end-of-day far red can reduce pigmentation, specifically anthocyanins in crops like lettuce. In this case, we found that that wasn't the case for our study. But where you often will see a greater decrease in pigmentation is when you're providing that far red light throughout the day. And you can see that pretty clearly as we start to look at this red oak leaf lettuce and how green those leaves look under that extended period of only receiving a low red to far red ratio throughout the day at a normal temperature. Where we did see the most promotive effect in terms of increasing anthocyanin content, though, was under reduced temperatures. And so we did find that if plants were growing under 18 degrees Celsius, we saw an increase in anthocyanin content, which you can also see if you look at the photos here, even just comparing end-of-day far red at 21 compared to 16, seeing that increase in terms of total anthocyanin content and pigmentation in the photos here. We did find, though, that colder nights, specifically that positive diff, did not increase anthocyanin content. It really seems like that temperature drop needs to still have some light as a response. The end-of-day light alongside that temperature drop did not result in an increase in anthocyanin content. But again, in this case, we found the end-of-day far red did not necessarily decrease anthocyanins. So mainly what I'm setting up here is that there was a lot of research that was done and a lot of questions that Anthony and I were asking and proposing to the LAMP team over the course of the years we were working. And what this ultimately led to was a lot of questions about what's driving these end of day responses. Why does it seem like under certain scenarios we get a great response in terms of end of day far red and getting leaf area expansion, and maybe under other environmental conditions it seems that we're not seeing those responses. Those responses may be somewhat restricted. And so that's what leads, and I'm going to pass off to Anthony to talk more about some of the factors that may be impacting how plants respond to, in this case, end of day far red, and some of the studies that he has planned and is currently running to help us to answer some of these questions. And the goal here is both to understand these responses, both from a physiological standpoint, but also to develop applications that are meaningful in the greenhouse. So with that, Anthony, I'll pass off to you. And we'll do a quick chair change.
Hi, everyone. So yeah, as Josh said, we had a lot of questions raised throughout our previous work, and a lot of it did boil down to what is affecting these responses to end-of-day far red treatment? Because species and cultivar-specific responses are kind of all over the map, but what's also been contributing to that is how plants are grown in different experiments. A lot of times they have different photoperiod lengths, they have different DLIs, they have different temperatures, and because all of these factors affect responses to far red radiation, it's really hard to pull out kind of like a general response that we can use to maybe make recommendations to growers who might want to implement this technology. Another thing that complicates it is the design of end-of-day far red treatments. Sometimes you just have one end-of-day far red treatment and a control. Sometimes the red to far red ratio of treatments doesn't really make sense. And sometimes people don't even investigate leaf responses, usually for good reasons. They're concerned with stem responses or something like that. But I have a lot of questions about all of these things, but I can't go through all of them. So I'm going to talk about the things I'm going to be investigating for the rest of my PhD. Which the first is species and cultivar specific shade avoidance or tolerance responses to end-of-day far red treatments. I'm just kind of weave that in throughout the rest of this presentation. And then I'm going to specifically focus on both the photoperiod and the DLI, kind of as like a joint project, and then how the red to far red ratio of end-of-day treatments affects responses. And I'm going to go through that one first, because that's the one I'm currently building right now. So as Josh kind of described earlier, the red to far red ratio is like a good approximation of the degree of shade. So as that red to far red ratio decreases, the degree of shade or how shady it is increases. And we see an increase in responses, shade responses, as that red to far red ratio decreases. We can also use percent far red radiation, where kind of the increase in far red percentage represents an increase in the degree of shade. And we see that same kind of treatment. So as the red to far red ratio decreases or the far red percentage increases, we get a more intense response. And a lot of work has been done on the stem responses because that's the most obvious and visible shade response. But less work has been conducted with leaves. There's definitely been some work that has shown that the red to far red ratio affects leaf elongation rate, leaf length elongation or width expansion. But it's few and far between, and a lot of the research is a little old, and so it could definitely use some refining. And then it's also important just to kind of restate that species respond really differently to far red light. So plants that grow as a rosette, they don't elongate their internodes, you might see a greater leaf expansion response because you don't see a stem elongation response. Where when it comes to plants that are growing upright, you kind of have to consider both the stem elongation response and the leaf expansion response. One might be beneficial while the other might be something you want to avoid, but that depends on what you're growing. So our first experiment that we have planned, the one I'm building right now, we're kind of asking the question is, how does the red to far red ratio affect leaf morphology? That says lead morphology, that's my bad. Leaf morphology. And we're going to be measuring the leaf morphological responses induced by end-of-day far red treatments that vary in the red to far red ratio. This is really kind of like the experiment that sets a baseline. Like, we know how the red to far red ratio impacts stem elongation. Let's nail down, at least for a couple species, how the red to far red ratio affects that leaf morphology. So we selected both some rosette species and some upright growth species that we're going to be able to use to compare those kind of different plant architectures. And we're going to be using image analysis in order to quantify leaf area so that we can also attribute the changes in that leaf area to specific morphological responses. So is the leaf area coming from a really elongated petiole? Is it coming from the blade of the leaf widening? Like, where are we getting that increase in leaf area? Because that matters in terms of just the plant growth and quality. And what we're kind of expecting from that is that a lower red to far red ratio is going to promote greater leaf expansion, but also stem elongation. So if you're trying to find a balance between the two, you might have to do some finagling. And then kind of the significance of this research is that as far red LEDs become more and more popular, people might start implementing them more into their growth spaces. And not all far red lights are the same. They might be outputting different red to far red ratios. So you may be getting different responses than your neighbor and not really understand why. So if we're kind of able to iron out how this red to far red ratio affects this leaf morphology for a couple species, it's gonna go, I think, a long way to start providing some guidance on how to implement these end of day far red treatment strategies, which I've already seen advertised by at least one lighting company. The next thing I'm going to talk about is the photoperiod and DLI and how those affect responses to end of day far red radiation. Just as like an overview, a lot of times in a lot of basic research with end of day far red as like the experimental kind of treatment, the plants are grown under really low DLIs. And sorry, let me start that over. Actually, I'm just going to go to the next slide. So we know that responses to far red radiation are dependent on PAR or EPAR. So like the amount of far red you have is going to interact with the amount of red, green, blue, and UV light. Because natural shade is comprised of low red, green, blue, and UV light and relatively high far red light. And we can do experiments in the lab where we're looking at both light intensity, which is on your y-axis here, and the percent of far red radiation. And what we can see is as you increase that far red percentage, you get an increase in the stem elongation. But if you suddenly bump up the overall light intensity and then look at some of these elongation responses, they're not as pronounced as when grown under a low overall light intensity. And you can see the same thing when it comes to leaf area or leaf expansion. For cucumber, as you increase that far red percentage, you're getting increased leaf expansion. But this leaf expansion is a whole lot greater as you jump up to these higher light intensities. And so the thought for us is, if responses to far red light applied throughout the day depend on that background radiation, responses to end of day far red light probably depend on the DLI, at least in part, that a plant has accumulated throughout the day. So how much light that plant has gotten throughout the day. And we know from past research that either a high DLI and or a long photoperiod can limit stem elongation responses, which you can see in this figure here, where Arabidopsis plants are given either a long day, LD, or a short day, SD, and then either an end of day far red treatment or no end of day far red treatment. And the end of day far red treatment has relatively little effect on the hypocaudal length of Arabidopsis plants under that long day, but under that short day, you see this rapid jump in hypocaudal length. So that's one reason that photoperiod and or DLI might matter. And I say and or because it's hard to separate DLI and photoperiod, because as you increase the photoperiod, you increase the DLI. As you decrease the photoperiod, you decrease the DLI. And it's also known that there are plant circadian rhythm responses that affect general sensitivities to light qualities. So we want to look at this from both like a practical perspective, the DLI and photoperiod, but maybe also look into some of the circadian rhythm stuff. And then just kind of as a point to close this, a sufficient DLI may be required for leaf expansion in response to end of day far red, just as it may be required when far red light is applied throughout the day. I have like one example of Arabidopsis thaliana, where when it's grown under a high DLI, you get increased leaf area, but when it's grown under a low DLI, which is much more common in end of day far red experiments, you get that reduced leaf area. So I know I'm getting close to time here. So our second experiment is just going to be looking at, do DLI and photoperiod impact end of day far red responses? So we're going to use the same plant species as of now, but we're open to definitely suggestions for plants to trial with this. We're going to try to measure the main and interactive effects of DLI and photoperiod on responses to end of day far red treatment. So to do that, we're going to have both a high DLI treatment and a low DLI treatment, where in both, plants are either receiving a control, no end of day light, or end of day far red. And we're also going to be doing that at 8, 12, and 16-hour photoperiods. So we can look at both the main and the interactive effects to see the relative importance of these two different environmental parameters. And kind of like previous research has shown, we're expecting that a low DLI and short photoperiods are going to facilitate that stem elongation, where a high DLI and longer photoperiods are going to facilitate that leaf expansion, but also maybe stem elongation for some of those upright growing plants. And then kind of the significance of this project is that the DLI and the photoperiod are not constant throughout the year if you're growing in the greenhouse. You can manipulate it to some extent, but there's only so much you can do. So if we can look at these responses at different DLIs and different photoperiod lengths, it might help a grower decide when during the year it's most effective to implement these treatments. That's where I'm going to stop and let Josh take it back and just close out with some summary points.
One last summary point. And this is really just for growers that are looking at, what are the takeaways here and what do I now do in my greenhouse? And really, end-of-day far red we know can promote significant morphological responses. And these responses are dependent on potentially many different things. It's the species-specific response, the red to far red ratio, it's potentially your photoperiod and DLI, like Anthony was mentioning, which we've seen in his previous work as well. And so right now, as we look at an end-of-day far red response, do we have recommendations? No, that's something that we're hoping that we can develop in the coming months as we continue this research. And so Project LAMP has really provided a nice foundation and a lot of good questions that we've had as a group to then say, where does this lead and how can this help us to develop really good protocols and really good applications moving forward? And so there are some great resources out there already about end-of-day applications for things like hypocotyl elongation, if you're looking at things like grafting, but in terms of like leaf area responses and some of these plant quality responses, there's a lot that we still need to do to really understand how we can leverage current technologies that are being developed in the greenhouse. I think the most important one for growers right now, though, is just to use caution when you're using far red light if your PPFD is consistently low. What we're seeing is that those low DLIs, those low light intensities, if you're providing even a small amount of end-of-day far red light, that can lead to some undesirable shade avoidance responses that could reduce the quality of, in this case, for example, like you saw in some of the previous work, things like bedding plant seedlings. And so I know we're a little bit over time, so I want to wrap up here and acknowledge just amazing resources and lab as well as Project LAMP just for the wonderful work we've been able to do with them over the past few years. I'm happy to answer questions, but also want to take a moment to just pause and pass this off to Jorge so that we can.
Okay, we have time for a couple of questions. If anybody has any questions, please go ahead and it's Josh or Anthony. Thank you.